Hello, this is a companion video to my solar panel solar generator review. This slide stack is going to cover my initial thoughts and what I learned as I assembled the components to put my solar powered generator together. First off, a disclaimer. I'm not an expert. Everything that I am presenting here I learned on the internet. Use this information at your own risk. So first off, why did I decide to build a solar generator? I had some basic questions. What was I going to do if the power went out? What kind of generator would I need to power the home? And how much gas would that take? I really didn't have a power strategy, and believe it or not, my wife actually made us take a microwave camping with us, so I wanted to see if I could make this solution portable. As I did some research, I discovered numerous solar power vendors, and I have listed them here. The two that I'm going to use for reference are SolarStick and GoalZero. These represent both ends of the spectrum. GoalZero makes a great consumer product, and SolarStick appears geared to the high-end professional. When you look at the costs, including solar panels, batteries, controllers, and inverters, SolarStick appears to be ranging from $5,400 to $6,700. GoalZero is a much lower entry point, but you have to purchase additional add-on items to achieve a comparable solution to SolarStick. These prices were obtained via public web pages, so you may be able to find them cheaper. My initial thought was this is not cheap. I did not have $1,800, let alone $5,000 lying around. My gut reaction was to go to Lowe's or Home Depot and buy a larger generator and more gas for under $1,000. But then on second thought, gas isn't really renewable, and in a disaster scenario, would I be able to get some? So I started thinking I could build this. As I started to look at the different components that the vendors were using, I realized a majority of them were used in campers, motorhomes, and sailboats. One could actually purchase these components and build it themselves. I came to believe that I could build this myself. Now, being a guy, do not fall prey to Tim the Toolman Taylor. Bigger isn't necessarily better. Larger batteries or more batteries will give you more capacity, but will also dramatically increase the size and weight. Here are the basic components of a solar system. Obviously, you need solar panels. You need some sort of charge controller to take the power from the panels and charge the batteries. Generally, controllers come in two varieties, MPPT and PWM. MPPT being better but more expensive. Batteries are rated in amp hours. The drawback to getting more or larger batteries is they get heavier to port around. You are then going to need an inverter for AC or a DC distribution panel. Inverters come in two flavors, pure sine wave and modified sine wave. Pure sine wave more closely resembles the smooth power curve that comes out of your outlet. Modified sine wave is still a little blocky. Numerous high-end electronics do not perform well with modified sine wave inverters. If you have high-end computers, televisions, or medical devices, you are better off paying the extra money for the pure sine wave inverter. As you put all the components together, you are going to need fuses, switches, different gauge wire, along with a box to put everything in if you want it to be portable. So here is the basic math formula that you're going to need to know. Amps times volts equals watts. Now your batteries are measured in amp hours, meaning a 100 amp hour battery can provide 100 amps for 1 hour, or 1 amp for 100 hours, or 25 amps for 4 hours, or any similar ratio that gives you 100. Think of it as a bucket of water of a set size. You can pour it out fast, or you can pour it out slow. Solar panels are measured somewhat the same, but a little different. They are measured in watts, amps, and volts. For my design, I use 12-volt panels. You also have the option of configuring your panels and batteries in series or parallel. What that means is that if you take two 100-watt solar panels and put them in parallel, you get 200 watts at 12 volts. If you put them in series, they stay at 100 watts, but you jump to 24 volts. And that's how you get the different solar systems running at 12, 24, and 48 volts. The advantage of parallel is a little bit of redundancy. If you lose a panel for some reason, you still have power, but at a lower wattage. If you put them in series and you lose a panel, you lose everything. This is why you will often see parallel and series in combination to give redundancy. In my design, I used parallel. The same applies to batteries. If you take two 100 amp hour batteries and put them in parallel, you now have 200 amp hours. If you put them in series, you have 100 amp hours at 24 volts. But again, if you lose a battery in series, you lose everything in that series. So what does all that mean? Basically, there are three questions to answer when designing a solar power system. First, what do you want to power and for how long? Second question is how long will it take to charge your batteries? And the third question is how long will it take to drain your battery? Again, think of the battery as a bucket full of water with a hole in the bottom. The hole in the bottom is what you are providing power to, and at the top you are pouring water back in with your solar cells. You have to pour water in faster than you are pulling the water out. Otherwise, you're going to end up with a dead battery. Here is the math part 2. Once you know how much power you need to double it. Batteries do not like to be drained more than 50%. If you think you need 100 amp hours, you actually need 200 amp hours. If you are planning for redundancy, this just means two batteries the same size in parallel. When it comes to charging the battery, multiply by the time by 2. Remember the bucket with the hole in it. You have to put more in than you are taking out to charge back up and account for days with limited sunshine. This is what I call the powers of 2. You need twice your budget in batteries, and you need twice the time to charge or charge twice as fast to always be recharging your batteries. So here is the practical example of SolarStick, Goal Zero, and then the system that I put together. SolarStick has two 50-watt panels in parallel for 100 watts and two 45 amp hour batteries in parallel for 90 amp hours. They also sell it with a 180 watt inverter. So doing the math, it would take about 2.7 hours to drain it down to 50%, which is where you should stop, and about 11.7 hours to charge it back up. Now this is assuming that your inverter is 90% efficient and your solar panels are 66% efficient with 6 prime hours in the day for charging. Now SolarStick and Goal Zero can reposition the panels as the sun moves, and SolarStick is using an MPPT controller, so the efficiency should be a little bit better. These numbers are approximation for comparison only. Your mileage may vary. The Goal Zero solution has two 30-watt panels and one 100 amp hour battery, so less redundancy. It would drain to 50% in 3 hours, but take over 23 hours to charge back up. They sell it with a 1200 watt inverter, but using this large a load would drain it even quicker, and you would still have the long recharge time. If you look at the system I put together, I had two 140 watt panels in parallel for 180 watts and two 104 amp hour batteries for 208 amp hours. I had a 1500 watt inverter, but using the 180 amp inverter, it would take 6.2 hours to drain to 50% and almost 10 hours to charge back up. So I need a third panel to reduce this charge time. Now a note on portability. SolarStick and Goal Zero's battery banks weigh about 60 pounds. Mine is a little over 130. This does not take into account the added weight of the larger solar panels and inverter. So while I win in the power and charging areas, I am losing in the portability. So, how to put it all together? Or where should I have started if I could do it all over? First, decide what you want to power and for how long. How many lamps do you need to light in your house? Will the internet be up and should you power a computer? Will you need a TV to watch the news? One way to do this is to purchase a watt appliance load tester or a kilowatt tester from Lowe's or Home Depot and measure the watts and amps used by each device, and then build a power budget based on how long you are going to power each device. From that, you'll be able to size your battery bank, solar power panels, and inverter. Here is what my power budget is. 1 lamp for 2 hours, a laptop for 5 hours, a television for 5 hours to check the news at morning, noon, and dinner, and late evening, the cable, if the internet is working. I have a large antenna, so I'm not dependent on it for television. Then the refrigerator for 2 hours after each meal, and then the microwave to help with meal preparation. Now, if you do the math and you add everything up, I need 4,203 watt hours in my battery bank, and an inverter that can handle 2,475 watts if everything is on at once. So here is where we size the batteries. We do the math taking into account efficiencies and come up with 389 amp hours, which multiplied by 2 equals 780. But if I choose not to power the laptop, microwave, and refrigerator, I would only need 100 amps, which multiplied by 2 is 200. I have 208 amp hours in my design, so I am okay here. For the inverter, I needed 2,500 watts, but I only have a 1,500 watt inverter. Again, if I drop out the laptop, microwave, and refrigerator, I only need 275 watts. This gets me back to a safe level. Now we need to size the solar panels. I need to have between 100 and 389 amp hours. And again, I need to be able to provide this power and put power back into the system. I need to account for days when there may not be sunshine. I can't simply maintain the status quo. I need to put back in more power than I am taking out. So I multiply by 2 to get 200 and 780 amp hours. I then divide by 6, assuming that there are only 6 prime hours in the day for charging. This gives me 33 to 130 amps. I then take into account that my panels might be charging only 66% efficient, and I need my solar panels to generate between 50 and 197 amps now. Applying the watts, amps, volts equation, I find I would need between 603 to 2,358 watts of power from my panels. This would be 4 150 watt panels or up to 16 150 watt panels. This would also drive me into a more complex solution requiring multiple controllers running at 24 or 48 volt. So, what should I have built? If I want to power everything, I need 4 200 amp hour batteries. I have 2 104 amp hour batteries. I would need a 2,500 watt inverter. I have a 1,500 watt inverter. And I would need 16 150 watt solar panels with additional chargers and controllers. Now, if I decide not to try and power the laptop, microwave, refrigerator, my design requirements become as follows. 2 100 amp hour batteries, so I'm okay here, a 300 watt inverter, which I'm okay there, and 4 150 watt solar panels. I can add a third 140 watt panel without having to upgrade my controller, so I can get a little bit closer there. But what about the laptop, microwave, and refrigerator? I actually have a small 2,000 watt Honda generator that I plan to use to power those devices during breakfast, lunch, and dinner. I will also use it to power the refrigerator for 2 hours after each meal and chill everything back down. The laptop will also be connected to the generator at this time to power it and to recharge its battery. My generator at full load only uses 1.65 gallons a day and 50 gallons a month. I should not be using it at full load, so hopefully my usage will be less. At today's gas prices, that would be $175 a month. In an emergency, gas would get more expensive and harder to find, but I could lay in a month's supply fairly easily if I planned ahead. So, what did I learn? First, this is still not cheap. Start by doing a power inventory. From that, create a power rationing strategy. What do you really need to power and for how long? You may need to have technology-free days so your batteries can catch up. Use solar-powered radios for communication. Purchase a small solar panel for charging phones, iPads, and batteries for the children's toys. Make them responsible for managing their own power budget. Finally, combine solar power and a small generator. This will allow you to keep the size and weight of both manageable if you want a portable solution. Thank you for watching. Please send me your comments and suggestions, and as always, please subscribe.